Do you see the presentation number 2, which is covering Model 1, background on POPs contaminated site, and Model 2, principles and approaches for POP contaminated site management? Here you see the name of Lee Bell and myself. Lee Bell is from IPEN, and he has been the co-editor of the guidance, and I did that activity as IAPA member. And IAPA is the International HCH and Pesticide Association. So the content of this session is the objectives of this session. I give a general introduction on the sustainable management of POP contaminated sites, going a bit into details on the principles, the objective, and the content. Then I have a special slide related to the relationship between the Stockholm and the Basel Convention regarding POPs waste and contaminated matrices. And then I will explain Model 1, background, POP contaminated site, and Model 2, principles and approaches for POPs contaminated site management and remediation. So the objective of this session is to introduce the best available technique and the best environmental practice guidance to sustainably manage POPs contaminated site, Stockholm Convention. The link here again, and it has 5 phases as I explained earlier. The principles are the principles of the sustainable management of contaminated sites, and it counts also for contaminated sites, not only for POPs, but also for heavy metals, TPH, and others. The principles is that it should have an holistic approach. It employs strategies for cleanup that use natural resources and is energy efficient, reduce negative impacts on the environment, minimize or eliminates pollution at the source, protects and benefits the community at large. So it should not only be focused on the removal of contamination, but it should have an approach, that has no negative impact on the surroundings, is cost effective, and is guaranteed that results sustain in the future. And it should have the next principle, is sustainability, characterized by precautionary principles, intergenerational equity, and polluter pay principle. So meaning that intergenerational equity means that you should not leave contaminants to your future generation. The other principle is developing site-specific target levels, dependent on the intended site use, and these may vary per POP type or a combination of POP contaminated, meaning that if you have a site which will be in future a playground for children, then of course it should be very clean. If you have a site that will be used in future for industry, then the levels can be higher. So the target levels to remediate should be site specific. That means also that what you can reach also determines the future site use. You can also turn it around. Then contaminated groundwater should be treated to restore the highest level of functionality and minimize contaminated levels. So for groundwater, you should do the utmost efforts to clean, as groundwater of course moves in the soil and goes offsite. So this is a different approach than soil. Soil is adapted to the site use. Groundwater contamination should be restored to the highest level possible. Then the other principle is a risk-based approach for soil. So functional soil should be conserved wherever possible for ecological and economical reasons, as its POP concentration should be lowered to the level below acceptable risk levels for potential receptors by sustainable management and remediation techniques, meaning that you should look at a site, and when it has risks, you should try to remove the risks. But removing the risk can be done by taking away the source, cut off the pathway, or protect the receptors. And depending on the site use, you do either one of these 3, and then the site-specific target levels come into action. And then a very important remark, contaminated soil is only waste when it has lost all its soil function. So contaminated soil should not be treated as waste unless it has lost all its function. If POP's contaminated soil has lost all its function and is deemed POP waste, it should be subjected to Article 6 of the Convention of Stockholm and the Basel Convention POPs. So then that means that it should be treated as waste. So what are the objectives of the sustainable management of contaminated sites? I mean, it's very clear. Protect human from contact with contaminants. And you can have direct contact, dermal, swallowing and inhalation, and indirect contact through food chain and water. The objective is of course also to protect the ecosystem or the environment, to protect soil and groundwater from getting contaminated, protect drink water resources from getting contaminated, and protect surface water from getting contaminated. And then the last objective is to prevent migration of contaminants. Prevent migration to become airborne, dust, prevent contamination to run off when heavy rain comes and then erosion processes take away contaminated soil offsite, and prevent contaminants to leach into the soil or groundwater. So by rain and by irrigation, contaminants can leach into the soil and finally reach the groundwater. So these are the objective of the management of contaminated sites. Here is the slide illustrating the relationship between the Stockholm and the Basel Convention guidance regarding POP waste and contaminated matter. So this first text box here is the Stockholm Convention and this is the Basel Convention. The Stockholm Convention and the guidance on the management of POPs contaminated sites is dealing with POPs contaminated sites. And on POPs contaminated sites, you can have different site components like POPs contaminated soil, POP contaminated groundwater, POP contaminated sediments, bottom sediments in waters and rivers, sea, POPs contaminated building material. You can have a storage facility which is used to store POP pesticides or other chemicals, and they have been leaking, and then the floor is being soaked with contaminants. And then on a site which is POP contaminated, you have also your POP waste, and if it's not POP waste, you can also read here chemical waste. The remediation of a site covers with the remediation of soil, groundwater, sediment, and buildings. The remediation processes for POPs waste is only to repack, and then it immediately is subjected to the Basel Convention. But if you do remediation, you get residues from the treatment of soil, groundwater, sediment, and material. And this residue should treat it in line with the Basel Convention. So I hope this is clear. So the Stockholm Convention deals with the contaminated site, and from the contaminated site you may have waste, and waste is treated in line with the Basel Convention. Any questions on this? Because this is an important issue, and this has the relation with the earlier remark that as long as soil has not lost all its soil function, it should be remediated. If it has lost all its soil functions, then it is subjected to the Basel Convention. Any questions on this? Thank you. Thank you. Model 1, background on POPs contaminated site. The table of content of this guidance or this model is introduction, threshold levels for POPs, legal and technical issues are discussed that defines a contaminated site. So when is a site a contaminated site? And then we discuss the comparison of soil sampling data with background levels, the comparison of sampling data with soil screening levels, and site-specific screening levels and risk assessment. And here again, the risk assessment is the basis for the management of contaminated site. And based on the site use, you have site-specific screening levels. And then Model 2 also go into a bit more details on fate and transport of POPs. We do not cover everything. I mean, there are a lot of textbooks on fate and transport, but we cover a part of it. And we have in every model, we have references, and you can consult these references if you want to have more information. So this is the table of content of Model 1. Defining contaminated site. The objective of Model 1 is to assist policymakers and regulators to consider key elements in developing, updating their national definition of contaminated sites. So it's very important to have a definition of a contaminated site to be able to remediate site under your legislation. Model 1 provides also a general background on the issues of POP contaminated sites and explains the rationales behind definitions of a contaminated site and provides some examples. So in this model, we provide examples of contaminated sites from different countries. But defining contaminated site is a combination of legal, technical, and social elements that includes the use of threshold or screening levels for POPs in soil, sediment, and groundwater to determine if a site meets the technical definition of contaminated. So that may differ. That may differ depending on the site use and depending on the future site. Legal elements of definition may mandate how much a site should be treated, whether and how ownerships may be transferred, and how and who is responsible for the management and how that is conducted. Then the social elements of definitions may refer to land use, permit different levels of risk according to whether it is residential, commercial, or industrial. So the land use determine also if a site is contaminated. As I said earlier, if it is a playground for children, the levels acceptable in the soil should be to a minimum. So that determines that if a site is contaminated for a certain site use. Finally, Model 1 describes the characteristics of key POPs in terms of fate and transport and how they are behave in soil and groundwater during degradation and how this is relevant to the management and remediation of the sites. So fate and transport, to understand fate and transport of your contaminants of concern in the soil is important to understand the situation on site, and the understanding is reflected in your conceptual site model. And here is a list of fate and transport processes in soil. We can divide the fate and transport processes in soil between physical processes, chemical processes, biological processes, and anthropogenic activities. But let's continue with the physical processes. Infiltration, movement of water from the surface into the soil. Percolations, downward movement of water through soil layers to the groundwater. And then, of course, it can uptake contaminants. And this is the way how soil is being contaminated by percolation. Runoff, water flow or erosion on soil surface when infiltrating capacity is exceeded to whatever reason, meaning runoff can migrate contaminant soil particles to elsewhere. Evaporation, water and volatile component loss from soil to the atmosphere. So water can be evaporated, but of course also volatile components can be evaporated from the soil. Transpiration, water uptake by plants and releases through leaves. This is also a pathway of a possible pathway of contaminants. And this is also important to consider in remediation processes, and especially phytoremediation, so remediation by plants. Then capillary activity, upwards movement of water due to the surface tension, including the uptake of contaminant groundwater. Diffusion, movement of gas or solutes from high to low concentration. And this is also a migration pathway of contaminants. Affection, transport of solutants to heat with flowing water. So when the temperature changes, this process is being enhanced. And this is also important to consider in remediation processes. Sedimentation, settling of suspected particles in water. So particles, including particles that are soil particles that are contaminant, can be settled in the soil by sedimentation. Erosion, soil erosion, detachment and transport of soil by wind and water. That's a general process, and of course, that is relation with runoff. Recharge, replenish of water from surface water. So if surface water is contaminated, it can be a process of soil contamination. Seepage, slow escape of water from soil or aquifer. This is also a pathway of contaminants. And aquifer flow, the groundwater flow, lateral movement of groundwater within the aquifer. This is also a pathway of contaminants. These processes all contribute to the remediation of to a site to get contaminated. And these processes can also be used to remediate. So understanding of the processes that takes place in the soil is a very important aspect of site investigation and site remediation. But besides the physical process, we have chemical processes. Ion exchange of ions between soil particles and water, sorption and desorption, attachments and releases of substances, including nutrients and contaminants to soil particles. And sorption and desorption can be in the soil particles, in the clay mineral, and at the particles, so around a film, around a soil particle. Then you have precipitation and dissolutions, formation or dissolving of minerals and salts. That's clear. And this can be also in the contaminants. Redox reaction, oxidation or reduction of elements from iron 2+ to 3+ nitrogen to nitrate to nitrogen. And these processes are being considered in remediation, especially in situ remediation. Hydrolysis, reaction of minerals with water and breaking chemical bonds. Carbonization, reaction of CO2 with water and mineral forming carbonates. Acid-base reaction, neutralization of pH and regulation processes. Neutralization and pH regulation processes. It's an important aspect because if the pH change, the mobility of certain heavy metals may change. An example is, for instance, arsenic. When the pH is high, it becomes more mobile. So it's important to know what the pH is and what the relation is between your contaminant of concern, especially when it's concerned heavy metals. Salinization, binding of metals by organic modules, making them more mobile, and weathering, breaking down of rocks and minerals. And this is important to consider because your background values in groundwater may be influenced by this weathering. Any questions on the processes? Okay, biological processes. Decomposition, breakdown of organic material and other components into simpler compounds. That process is constantly taking place into the soil, including the breakdown of decomposition of contaminants. So if you have a contamination entering into the soil, it breaks down, and it can break down into more toxic components and less toxic components. So you have to realize what happens with my contaminants in the soil. Mineralization, conversion of organic nutrients into inorganic forms. Immobilization, incorporate of organic nutrients and other components into microbial or plant biomass. Immobilization is an important aspect. You have your absorption complex in your soil, and your absorption complex in your soil is your organic compound, your organic material in the soil, and your clay minerals. This is your absorption complex of the soil, and they partly immobilize your contaminant. So considering and knowing what your organic content is and what your clay content is in the soil is important. In Holland, we have reference levels, and these reference levels are based on the organic content in the soil and the clay content in the soil. So when the clay content and the organic matter content is higher in the soil, we accept higher levels of, for instance, heavy metals in the soil. Other biological processes are nitrification, ammonium to nitrate to nitrate, denitrification from nitrate to nitrogen gas, nitrogen fixation, conversion of atmospheric nitrogen to biological available nitrogen. This is also taking place by plants, the plants which have leguminose. Then we have metachonesis, production of methane in anaerobic condition, sulfate reduction, biofilm formation, colonization of soil and aquifer servants by microcommunities, and reservoir processes, microbial and chemical activities influenced by plant roots. This is a process which is used in the phytoremediation. Then the last group of processes influences by this influences soil and groundwater, which is anthropogenic activities. Irrigation, drainage alters water balance and salinity. Fertilization and pesticide application introduce nutrients and contaminants in the soil. Land use changes may affect erosion, compaction, and hydrological characteristic may change. Contamination by industrial processes, leaching of heavy metals, hydrocarbons, solvents, and so on. And then groundwater abstraction can lead to depletion or land subsidence, but also to the migration of contaminants. So these are the fate and transport processes to be taken into account if you are investigating a site. And knowing this is important to take the appropriate remedial actions, the risk reduction actions. So here is a picture illustrating not all, but a few important processes. And this is from a book by the Tau company. It's called In Situ Soil and Groundwater Remediation Theory and Practice. Here's the ISBN number. It can be obtained from their website, Tau, and it gives you detailed information on the fate and transport of contaminants in soil in relation to in situ soil remediation. And I would advise you, if you are doing remediation, and especially in situ remediation, to consult this textbook. It's used in universities. This was, in short, the content of Model 1. Model 2 deals with the principle and approaches of POPs contaminated site management and remediation. The table of content. After introduction, we explain the risk-based approach. Then we go into section 3 in detail on the cost-benefit analysis. Then we discuss the multi-criterion analysis for remediation assessment. Then we discuss the green remediation and sustainable remediation. And then we bring it all together. And here in this module, we have an abstract written of the 5 phases I earlier mentioned. So phase 1, preliminary site investigation, had the first site investigation, then the detailed site investigation. So when there are risks discovered in the first phase, you have to step into the next phase, which is the detailed investigation. And if the risks are confirmed and are unacceptable, you change to phase 3, the site remediation assessment, selecting the best remedial option. And then with this best remedial option, you enter into phase 4, which is the remediation itself. So the digging, the installation of in situ remediation, the pump and the groundwater pump and treat, and so on. And then phase 5 is the site monitoring and aftercare. Often the remediation is carried out in phase 4, then you have remaining risks. And these remaining risks should be monitored and taken care of to sustain the remediation result accomplished in phase number 4. I mean, we have many sites in the Netherlands where we carried out remediation, but that has still remaining risk due to remaining contaminants on site, which were not able to be remediated due to cost or technical limitations. The objective of Model 2 are to clarify what green and sustainable management of contaminated site is, to clarify risk-based approach, to clarify a holistic approach considering associated economic, social, and cultural issues. The other objective is to highlight the difference between POP-contaminated site and sites contaminated with other chemicals of concern. And it explains the importance of including social and cultural values of ethnic minority groups directly affected in the cost-benefit analysis. So the cost-benefit analysis should not only consider technical issues and the cost for technical issues, but also the social and cultural values of especially ethnic minority groups. And Model 2 also introduced a stepwise or phased approach of the sustainable management of contaminated sites. Green and sustainable management of contaminated sites, the principle of sustainable use are part of the approach principles of integration. So you have to integrate economic development, social development, and environmental protection. So meaning that if you are going to develop a site close to an urban area and you want to expand your urban area, you have to take into account this economic development and see if it is possible to have in future, for instance, urban area. If not, you cannot change. You should adapt your development to the possibility of remediation. And this, of course, have a lot of a relation with the available budget for remediation. Then precautionary principles, meaning that you have to take care of your site by precautionary measures to not remediate. So monitoring and aftercare when you installed underground storage tanks, make sure that they are intact, that they're not leaking, and that you monitor the site that there are no new contaminations are being generated. Intergenerational future and intergenerational. So meaning that you have to take care that you do not bring the contaminants to the next generation, and that you have your approach also being adapted to this situation on the site and not affecting groups besides the site user. For instance, if you have an installation on site, you make sure that the emission of your activity is controlled and not, for instance, by wind taking dust to a neighboring site. Then another part is the conservation of biological diversity, ecological integrity, and internalization external hidden environmental cost. So here it means that the one who is pollutant, who is the polluter, should pay for it. This is the polluter pay principle, which is in principle the basis for the financing of remedial actions. This is of course not possible in many cases, and then the government has to step in and develop financial instruments to finance the remediation campaigns. I will come to that in a later phase. Risk-based approach. Sorry, are there other questions on my last part? Okay, we are with the Model 2 risk-based approach. In principle, economic costs for remediation are high. It's an expensive exercise. They can dump installation of in situ installations are costly. And one of the aspects that cost money is that for a long time you cannot use the site as you want. So the principle is to maximize the benefit of the remediation using limited resources. Risk assessment of multiple sites to direct resources to those sites that present the highest risk. So meaning that if you are having budgets to remediate the sites, it's wise to carry out of this multiple sites, there's more than one site, risk assessment, and see which site has the highest risk, and there you bring your money to remediate, because your resources are limited. So address your limited resources to the high risk sites and identify the high risk site by risk assessment. And the same process counts for individual sites. If you have limited resources and you have an individual site which you want to remediate, and this you cannot remediate with the available resources, the full site, you address your limited resources to the high risk site component. And a site component is soil, groundwater, building. You can select on site the site components with highest risk. So risk assessment is an important tool for efficient use of your resources, of your limited resources. Another principle is the cost-benefit analysis, and you consider, besides risk, the economic value of performing various activities to reduce the risks, including the cost for the installation, the cost for the raw materials to be used, the transportation cost, and so on. So this cost-benefit analysis also assists with making broader decisions about the future site use. But cost-benefit analysis should not be the only tool to select the remediation measures, but also the multi-criteria decision analysis. And in this, besides cost, you also consider organizational, financial, juridical, technical, social, and administrative and environmental aspects. They all have influence on your remediation. So in a multi-criterion analysis or multi-criterion decision analysis, you consider all the different aspects to come finally with the best remedial actions, and considering all these aspects, these 7 aspects. An important aspect of the multi-criteria decision analysis is that uncertainties, which is often poorly accounted for in risk assessment, can be assessed and made explicit. So uncertainties in your approach should be considered. So you are, for instance, not very sure what the effect is of pump and treat actions. So if you're not sure, you should mention that and take that into account in your multi-criteria decision analysis. And when this uncertainty maintains, you may change your approach of the remediation. 2 ways to clarify or to deal with uncertainties is, again, go to the field and do additional survey, or change your approach that do not have these uncertainties.
Mr. Budwin, we have one question from Mohammed that is asking, can any of these principles be overlooked or ignored in case of severely contaminated sites due to the inability to control them and to achieve the best possible results? It's on the, if you go to the chat, he wrote the message there. I suppose that in a very extreme situations, if you can delete some of the things that you are mentioning, I suppose.
Okay, thanks for all the confirmation. Can any of these principles be overlooked or ignored in case of severely contaminated sites due to?
I suppose, like in a case like Fukushima, I suppose in the high extreme, so after, I don't know, some bombardment or something.
Yeah. But for instance, the flooding in Libya last year. I think the question it's a good question, and the answer is, of course, not easy. But I think that's the most important tools of addressing a contaminated site is to try to get as much as possible to form your idea of what is happening. And of course, it's difficult to overlook things or not have the information. But that's the uncertainty I just tried to explain. The uncertainty should be formulated so that you are sure what you know, but also what you do not know, and take that into account when you design actions. So that you say, yeah, we want to do this, but we are not sure because that. I think having questions, having gaps in your understanding the gaps will always be there. But it is important to be aware of these gaps and not neglect them. Don't put them aside and say, oh, we don't know, we leave it. No, this is we don't know, but we proceed by this uncertainty. And in the process of developing your strategy to remediate or to take actions, you are aware of the uncertainty. And aware in such a case that you do not enlarge or that you take action to minimize this uncertainty. Does that answer the question, Mr. Mohammed?
Mr. Fogg, I must say that your answer was very well and concise. So I thought, yes, this is what I wanted to know. Yes, it was properly done. So thank you very much.
Okay. Okay, thank you. Okay, this was the last slide of the second presentation. I will go now to my next.